Pairwise similarity knowledge transfer for weakly supervised object localization. Supervised object detection training requires tedious data annotation. In this paper, we use knowledge transfer from a source dataset with full bounding box annotations to annotate new classes in a target dataset with weakly labeled images. In the first step of object localization, each weakly labeled image is first decomposed to a bag of several image proposals. In knowledge transfer setting, the proposals are generated by a faster RCNN trained on the source dataset. We solve the localization problem for each class in the target dataset separately. For class C, we split the target dataset into positive images which has at least one instance of class C and negative images with no instance of class C. By this definition, the problem of object localization is reduced to selecting one proposal from each positive image. In multiple instance learning, this selection problem is solved by jointly learning a unary score psi and a binary label y for each proposal E. The labels are constrained such that exactly one proposal has label 1 in each positive bag, and every other proposal has label 0. This constraint set is represented by F. Here, bold Y denotes the vector of labels Y for all proposals. In this framework, unary scores and labels are learned jointly using alternating optimization. In knowledge transfer setting, this optimization is guided by an agnostic objectness measure learned from the fully labeled source dataset. In this paper, we argue that using only the objectness is a weak form of knowledge transfer, and propose to additionally transfer a pairwise similarity measure that compares pair of proposals. We also learn pairwise scores and binary pairwise labels from the target dataset. We define constraint set A to make sure pairwise labels remain consistent with unary labels. Here, vector Z is a concatenation of unary and pairwise labels. We define the overall loss as a weighted combination of the multiple instance learning loss and the newly introduced pairwise loss. Similar to the multiple instance learning approach, we optimize the overall loss by a two-step alternating optimization. In the first step, called retraining, we learn unary and pairwise similarities given current unary and pairwise labels. This step is straightforward and can be done using stochastic gradient descent optimization within any deep neural network learning framework. In the second step, called re-localization, we optimize the labels given the current unary and pairwise similarities. We find out if the sigmoid cross entropy loss is employed in the loss function, this optimization is actually a linear program. To see this, we decompose the loss into three terms. The first and second terms are the loss defined on the positive and negative images respectively. The last term is sum of the pairwise losses defined between positive and negative images. We notice that except for the first part, other terms remain constant for any feasible labeling. To further break down the first term, we observe that the sigmoid cross entropy loss is linear with respect to the input label y. Using this observation, we further simplify the re-localization objective. Again, the first term is constant with respect to the labeling. Therefore, the second term can be used as the objective for relocalization step. Interestingly, this term is linear with respect to the labels R and Y. Equivalently, the relocalization optimization can be shown in this vector form. Here, Z is the concatenation of vectors R and Y, and A is a feasible set of labels defined earlier. In general, any graphical model inference algorithm can be used to solve this linear optimization. However, state-of-the-art inference algorithms may not be applicable as finding an approximate labeling quickly becomes impractical as the size of positive images increases. This is because the number of pairwise labels increases quadratically with the number of positive bags due to the dense pairwise connectivity. Looking at different inference algorithms, we find out coordinate descent optimization methods like ICM are preferred for this application since they do not necessarily compute all the pairwise similarities. In each step of ICM, label of a single bag is updated while other labels are fixed. Therefore, ICM computes pairwise similarities only between the proposal in the current bag and selected proposals in other bags. Unfortunately, this is known that ICM is prone to local optimum and its performance is highly dependent on the quality of the initial labels. To provide a high-quality initialization to ICM, we use a simple approach in which the positive images are divided into multiple smaller subproblems, and the relocalization step is done over each subproblem independently using an efficient linear programming approach. This method is computationally efficient since we do not need to compute the pairwise similarities between subproblems. Although the optimization is done over few images, recent work on few-shot object localization suggests that the common object in each subproblem can still be localized with high accuracy. This allows to find a good balance between accuracy and speed by adjusting the size of subproblems. Finally, the predicted labels from this step are used to initialize ICM. We follow the same approach as previous work to incorporate the knowledge learned from the source dataset. We use convex combination of learned similarity functions in the last retraining step and the similarity functions learned from source dataset for relocalization. In our experiments, we first evaluate the performance of initialization method with different subproblem sizes. Note that this is the performance of initialization before applying ICM. As it's shown here, the correct localization performance increases by increasing the size of subproblems K, but at the same time the computational cost increases rapidly. Due to high computational cost, we do not increase K to more than 64. We use the labels from this experiment to initialize ICM and plot the correct localization rates and energy values over time. Markers are used to show the elapsed time between two epochs. As both core-loc and energy plots show, ICM converges to a better local optimum if subproblem size K in the initialization method is more than or equal to 4. Increasing K beyond 64 might still increase the results further, but it would be computationally expensive as the previous experiment suggests. As a rule of thumb, we should increase the subproblem size as far as time and computational resources allow. Finally, we run our full pipeline on ImageNet detection dataset and report the correct localization on the target set. Additionally, following the previous works, we also train a faster RCNN on the target set and report its mean average precision performance on a held out target test set. Comparison to the previous state-of-the-art shows by incorporating pairwise similarities into the multiple instance learning framework, the core-loc performance increases by 4% on the target set, and the mean average precision improves by 4.8% on the target test set. Here are a few selected results on ImageNet detection dataset. Here are some failure cases on ImageNet detection dataset. In most of the cases, our method fails to capture whole object. In other cases, the algorithm failure is due to visual similarities among multiple instances in an image. For more details and additional qualitative results, please read our full paper.